Good day, everyone. Welcome to our chemistry tutorials on Analogous TV. We'll be looking at chromatography. Now, part 2. Now, part 2 of chromatography, we're looking at TLC and column chromatography mainly. Remember yesterday, previous video, if I say yesterday, we looked at paper chromatography and we looked at special terms, paper chromatography. We look at definition. I said chromatography is to separate, isolate, or purify organic compounds, and the separation or the isolation is based on the different rate of migration. So if you have a mixture of substance in a particular material, let's say I have a mixture of pigments, I have chlorophyll, xanthophyll, and many other pigments. So I will separate them based on their rate of migration on the particular solvent. So, and the rate of migration, the migration is being carried out on the stationary phase. So I said the last time, I said if I have a stationary phase, so I'm going to, a solvent is going to move across the stationary phase. So if I have a mixture of three things A, B, C, A can travel to this distance, B can travel to this distance, C can travel to this distance. What is carrying A, B, C to travel is the mobile phase. Where they are being traveled on is the stationary phase. Yes, and we said for paper chromatography, stationary phase is water on cellulose paper or water on filter paper. We can use that also. Now, so paper chromatography is a type of liquid chromatography. Now, why I'm iterating on paper chromatography is because TLC chromatography, which stands for thin layer chromatography, is a special form of paper chromatography. It's just like paper, same principle, same process, same principle. But now in TSC, we are going to use a material known as a thin layer. And the thin layer is usually made up of silica. Yes, either silica or alumina. It's a material made from silica or alumina. It's a small material in the form of paper made up of alumina, made up of silica or alumina. Now, in TLC, I can have a test tube or a beaker, as the case may be. Then I'll put my thin layer material made up of silica or alumina. Now I'm going to draw a line. For TSC, we draw a line on the thin layer. Now when we draw a line, we put the solvent, which is the mobile phase, just below TLC. Just below the line on the TLC. So when we place solvent, let's say we have to separate A and B. Let's say we have to separate A and B. Remember, paper chromatography, which is a partition chromatography, works on the principle of solubility, which may be determined by polarity. Yes, solubility, which may be determined by polarity, because polar solvents are more soluble in, polar solutes are more soluble in polar solvents. Yes, non-polar solutes are more soluble in non-polar solvents. Now for TLC, thin layer chromatography, so we have a mixture of solvents, a mixture of solutes A and B to be separated. Now when we put A and B, you see the solvent traveling a distance on the thin layer. So the solvent can travel to this distance. So this place can be called the solvent front. We call it the solvent front. Such that the initial position of the distance of the solvent, the initial position of the solvent to the solvent front is called the distance moved by the solvent. Beautiful. Now, on TLC, it's more very familiar to paper and also resemble column chromatography in the sense that we're using a stationary phase that is made up of silica or alumina. So thin layer is stationary phase, yes. Thin layer in this case is stationary phase, a thin layer material made up of silica or alumina. Now, and silica and alumina is they are polar materials. Polar. Now, so what happens when separating A and B? Remember on the TLC, the solute between A and B that is more soluble in the solvent, the solvent can be non-polar or polar. So any of them that is more soluble in the solvent travels more. For it to be more soluble in the solvent, it means that if you travel more, that means it will be less absorbed or less partitioned or less traveled or less eluted on the stationary phase. So let's say the solvent we are using here is ethanol. Yes, we're using ethanol, the popular solvent. So I'm using ethanol. Now, let's say we use ethanol, and A is, let's use benzoic acid. A is benzoic acid, and B is, let me use naphthalene. Yes, B is naphthalene. Yes, naphthalene, sorry. Now, benzoic acid, naphthalene. Now, A is benzoic acid, B is naphthalene. Now, it is very obvious that benzoic acid as an acid will be more soluble in ethanol than naphthalene. Now, so what happens is that benzoic acid is more soluble. It means that benzoic acid will travel more on the solvent. So, to travel more on the stationary phase, so the solvent carries it traveling more, or it will elute more. So A is going to elute more on the by the solvent. It's going to be eluted more by the solvent because it is very attached to the solvent. Why is it attached to the solvent? Because the solvent is ethanol, which is more like polar. Benzoic acid is polar, so A will dissolve more. Naphthalene, on the other hand, might dissolve in ethanol, but the solubility in ethanol is less. It is less, and naphthalene will therefore be more attracted by the stationary phase. So naphthalene will travel a few distance. So if I should make this thin layer bigger here, let's broaden the thin layer. What I'm trying to say, let's say this is the distance moved by the solvent. So between, this was the solvent before, so distance moved by the solvent bar. Now it means that B will just travel a few distance and stop. It might create a band, stop there. Then the remaining, this A will travel more. Why is A traveling more? Because A is more soluble in ethanol. Yes. Now, because A is more soluble in ethanol, it will be less absorbed by the thin layer. So it will not be strongly absorbed by the thin layer because it's very soluble in ethanol compared to naphthalene. That's how we work on the thin layer. And remember, we have a value we calculate for every chromatography process for each of the solids. It's called the RF values, the retention factor value. Now, the RF value, please take note, is always less than 1. Always less than 1. So it is distance moved by the solvent. Let's say distance moved by the solute, pardon. Distance moved by solute so let's say A or B over distance. So distance moved by A or B by distance moved by the solvent. So the values of ROF, the retention factor values, are always less than 1. So that's how we work with thin layer chromatography. Now quickly, we'll look at column chromatography. In the next 1 minute, let's quickly talk about column chromatography. Now for column chromatography, on the other hand, it's an adsorption chromatography. Adsorption, because the stationary phase is solid. Yes, the stationary phase is solid. Column chromatography is an adsorption chromatography. Just very similar to thin layer, but this is the difference between, there are very few differences, very similar. Now for column chromatography, it works on the principle of polarity. Polarity is considered more than solubility. Yes, though TLC also works on the principle of polarity, or TLC and column, they are also similar. But TLC is a special form of paper chromatography. Now, for column chromatography, which can be used to isolate or absorb. Now, this is what we'll do. Now, we will make a packed column. Now, column chromatography, we make a packed column. So the column will be packed with some materials. Packed column. I'm going to pack the column. I'll pack the column. So make a packed column. Now, packed column. Now, I'm going to put an adsorbent. That adsorbent, the most popular adsorbent is silica gel. An adsorbent, a material that can absorb or absorb substances. An adsorbent, a solid adsorbent, making it an adsorption chromatography. Now, a solid adsorbent inside a packed column. Now, I can use alumina, I can use silica gel. Silica gel is the most popular. Now, for silica gel, it is a polar material. Silica gel is made up of silicon, made up of some silane. Yeah. Silica connected with 4 OHs. So basically, that's the basic structure, the basic substance in the silica gel. So this silica gel material is polar, the polar material. Now this is what happens in column chromatography. So in column chromatography, let's say I want to separate a mixture of B and C. Yes, B and C. Now I'll use an organic solvent as usual. So I'm going to feed the material, I'm going to feed the solvent to this point. So that the solvent point, so that the solvent, so I'll draw a line, I'll mark where the solvent was. So I'm going to put a line. Now watch. Now and in the solvent, I'm going to separate B and C. Let's say B is caffeine. B is caffeine. Caffeine is a nitrogenous organic compound. It's slightly polar. And C is 100% non-polar. C is benzene. Yes, caffeine is made up of nitrogen rings. Yeah, so it is slightly polar. So I use caffeine and benzene. I have a mixture of caffeine and benzene as B and C. I want to isolate. I want to purify it from benzene. So let's say benzene was used to dissolve caffeine. So I want to separate caffeine from benzene. So quickly, I want to isolate caffeine away from benzene. Now I'll put the mixture inside this. So I have B and C. Now to be observed that the solvent will travel to a particular distance called the solvent front. We said it before. So the solvent front. So this is solvent front. Beautiful. Solvent front. Now if you watch very well, if B travels with the solvent, C travels with the solvent. Now the traveling on the solvent is not based on the solubility in the solvent. Now the separation is based on the polarity. Now because silica gel is more polar, in column chromatography, silica gel is polar. Caffeine, which is more polar than benzene, will travel less because caffeine will be attracted to the stationary phase, which is silica gel. So caffeine just travels some distance, let's say here, and stop. C will travel the remaining distance here to travel a larger, to create a larger band. So I'm coming to band. So C will travel a further distance. Why does C travel a further distance? Because C is less attracted to the silica gel. Because C, why is C less attracted to the silica gel? Because C is non-polar and silica gel is polar. So the separation in column chromatography is based on the polarity of the stationary phase. So polarity is plays a big factor, playing a big role in column chromatography. So now in column chromatography, we observe is that there's usually creation of band. So B will create a band. So there will be there's a region on the stationary phase will just be B, a region on the stationary phase will be C. So at the end of the day, I can take this silica gel and bring it out here. And if you observe on the silica gel, I'm going to have a region of C and B. So I can cut this band and go and dissolve in a new solvent and extract B and extract C away from each other. So that is how we separate using the column chromatography. That's the basic principles of column chromatography. The organic solvent can be any non-polar solvent such as hexane. I can use the likes of ethers also. Hexane ethers can be used. I can employ ethanol, but please take note: polarity on the stationary phase. Polarity on the stationary phase of the stationary phase is the basic principle of separation of column chromatography. The organic solvent can be any non-polar solvent such as hexane. I can use the likes of ethers also. Hexane ethers can be used. I can employ ethanol, but please take note: polarity on the stationary phase. Polarity on the stationary phase of the stationary phase is the basic principle of separation of column chromatography. Until the next video, it's a bye for now. So I will advise you to subscribe, like, and share for more good content and more good videos on chemistry, and also our one-on-one interviews on chemical terms, chemical and biological terms or biological activities as it relates to human endeavor. So bringing doctors, bringing professors, ask them some basic chemical problem and possible ways to solve them. It is more like a one-on-one discussion interview on this channel. will commence soon. So stay tuned, like, share, subscribe, and share the videos. Until we see again, for now, it's bye.